Okay, welcome to this episode on denoising diffusion process for images specifically. So in this episode, we'll go through some more details that are more related to the problem of generating images. And by images, we mean something that has height, width, and maybe several channels such as RGB. Okay, so the forward process is basically an operation that allows us to generate a noisier sample. So when we go in the direction of destroying information, in most cases, we will want to start with a clean sample and generate a sample at a given t of the diffusion process. And that can be implemented basically as a linear interpolation between the two, following the equations from the previous episode. I've simplified the code here as AT and BT. These are some constants that basically derived using the equations, but the most important bit is that we're essentially interpolating each pixel in a linear fashion between x0 and noise or xt and noise, okay? So that's all there is to it. If we get our equations correct, if we set up the right schedule, we will get our forward process implemented in this way, okay? And more details will be available in this next episode where we actually have look into the diffusion fast-forward implementation and then proceed to running a notebook. Okay, so as for the schedule, a very common choice is a linear diffusion schedule. And there have been several alternatives proposed. And depending on some factors, they could be better or worse. But usually you can get things working even with something as simple as a linear schedule. But it's important to realize that this schedule has a very big influence over how much information is available at a given step of diffusion. If you don't do things right, you might have almost no information for most of your process, and that might be very difficult to train and also quite counterproductive. Okay, and at this point, I also want to make a quick mention of two works that have actually identified an issue related to the noise scheduling. And the key revelation here is that the amount of information destroyed in a sample is actually dependent on the shape, on the size of our image. So right here, we can actually look at the same level of noise used with the same exact same equation, but the low resolution samples look way more noisy than the high resolution. And that's because all this added noise is actually spread over many more pixels that carry shared information, correlated information. So even perceptually, it seems like there's quite little noise in the very high resolution sample and quite a lot of noise in the low resolution sample, even though they are all generated with the exact same noise level. And there are prevention mechanisms against that. And that's but what we will do for this course is essentially avoid this scenario by training in low resolution data. And for training in high resolution data, we'll use a different technique. Okay, but I just wanted to make this notice of the fact that there is definitely a relationship between the image size and the noise schedule. And if you want to train with very high resolution data, you might want to consider that. Okay, so for implementing reverse process, we essentially want to use our neural network to produce a sample at the previous step. Okay, so what we need to do is use a posterior params function that probably makes the use of the network. And that function will give us the mean parameter and STD parameter, and then we can just sample it as we sampled from a Gaussian distribution. Okay, so this is a very much simplified code, but here I'm just going through a very high level aspects of the implementation, and in the next episode we'll get more detail on how things are implemented exactly. And for training, all we need to do is define a method for our loss. So we feed in an image. We pick a random time step t from a uniform distribution. We you use the function forward step function to generate a noisy sample, and also we want the noise shape, which is the epsilon that we want to basically predict. We use our model to predict the noise shape, and then we apply a loss function between the noise, the ground truth noise, and the noise cut that comes from the neural network. And that's all there is to it. That's basically how we define the loss for training diffusion models. Now, for sampling, we need to, if we just do unconditional sampling, we need to define the shape of our data. And there is some flexibility here, like you can essentially pick any shape you want. Even if you train on 64 by 64, you might be able to generate some interesting samples with 128 by 128 or 32 by 32 shape. However, this generalization capability between different shapes in the most basic version of diffusion is a little bit limited. But still, you have this flexibility to define your input, the shape of your generated sample. You use a rand n function to sample from a zero mean unit variance Gaussian distribution, and that's basically the first state. So I actually x big T, but for simplicity, I used x small t name for the variable. And then what we want to do is actually go through every single step of the reverse process. So we reverse our range of known time steps, and we basically go from the very last time step, the very high index, to basically to the very low index of 0. And we use our model to predict the shape of the noise, and we use our sampler to based on that z of t, to predict the previous sample in the diffusion chain by following the reverse process. And at the very end, we return that sample, okay? Now, the last bit that's quite important for generating images is selecting the architecture. And what we first need to realize is that we will be mapping from an image of a given shape and with a given number of channels to the noise, to a vector that's supposed to approximate the noise present in that sample. So basically, we need to produce output that has the exact same shape as the input, okay? Because we're predicting the noise in that input. So UNet is a good candidate for that, and very often UNet with some additional features such as attentional residual blocks is used. And also the temporal embedding is quite crucial here, because at each step of the diffusion, it's usually quite useful to use this T argument for to make it a little bit easier to get the context of where we are in the diffusion chain. But with these small changes, UNet is very commonly used and seems to give a good performance. There are other attempts where transformers are used, such as these two papers. One is basically using a transformer in the latent space. The other one is actually proposing a fully transformer-based alternative to UNet. And now, finally, temporal embedding is directly inspired by the encodings that are being performed in transformers. We essentially do the exact same thing. So we have an encoding for each temporal step using sinusoidal components, and that's basically what it will look like. And it allows the network to get this context of where we are in the diffusion chain. Okay, so that's basically done in the exact same way. And that's it for this episode. In the next episode, we dive into the real code of Diffusion Fast Forward, and that will be followed up in the same episode. We will also run the notebook where you can train your own low resolution denoising diffusion model. And then later in the course, you will actually see how to perform high resolution diffusion, and you will also be able to run those in the Colab. Okay. So that's it for this episode, and I hope you stay for more. Okay.